Ladies and gentlemen, Assalamu alaikum, good morning. Before we start, I would like to thank the organizers for having given me the honor to participate in this conference. So let me now introduce myself. I am Kaoutar BABOURI, a second year PhD student in Material Science and Engineering at the National Higher School of Mining and Metallurgy of Annaba. My research topic is about analysis and numerical simulation of macrostructural and microstructural plastic anisotropy behavior of DN16 23ST14 steel sheet under associated flow rule approach before and after recrystallization, monitored by Dr. Najwa Matougi and Professor Walid Shahawi. This presentation is structured as follows. We will start by an introduction, a background, the objective of our study. Then we will discuss the methods used in this work, simulation, modeling, and experimental methods. Then we have results and discussion, and finally a conclusion. Let's start by the background. As you can see here, we have the problematic anisotropy of curved rolled sheet of our material intended for deep drawing used for the manufacture of tractor tanks at the level of the national company ETRAG, located here in Algeria in Constantine. Now the objectives. First objective is to predict mechanical behavior of our material via numerical model based on the plastic anisotropy. Second, to describe a qualitative and quantitative phenomenological study of the morphological texture of this material before and after static recrystallization. We can say that the aim objective is to better control the evolution of the anisotropy from a microstructural point of view in order to optimize the subsequent mechanical properties. Now let's move to the methods. It is important to understand the anisotropic mechanical behavior of the material in order to control it. However, the study of the anisotropy can be done as follows. First, by mechanical tests of uniaxial traction in different directions. Second, by characterization of the morphological texture of the material. Let's start by the first one. Mechanical tests of uniaxial traction in different directions. We have two methods, experimentally and via numerical simulation. Let's start by the experimental one. As you can see here, we have square sheets in our material. We did a microscopic observation to determine the rolling direction. After that, we used the laser machine to cut our specimens and the optical emission spectrometer to get the chemical composition of our material. Here we have our specimens cut in different angles, 0, 15, 30, etc. Now, the second method, numerical simulation. As you can see here, we have workflow simulation of anisotropic behavior. Here we present steps, but in brief. First step was to create the part. Second one, to add the properties of our material as shown here in this table. We have Young's modulus, density, etc. Third, we added our boundary conditions and the applied load. Then we have mesh, job, and finally visualization. As you can see here, we get our first result. Now results and discussion. We will start by stress strain curves for different strains. We will analyze the credibility of simulation. Analysis of the anisotropy of the stress tensor. Here we have stress strain curves, experimental and simulated. Okay, for 2%, for a strain equal to 2%. and here for 12%. We can understand that the first parameter indicative of the mechanical anisotropy is that of the distribution of the stress transfer along the three angles. At the elastic limit, where we observe a quite remarkable deviation for the 2% rate and less important on the 12%. The anisotropy is also more pronounced on the experimental curves than the simulated ones. Now, let's move to the calculation of normal and planar anisotropy. We use those equations and we get those results represented in this table. Experimental and simulated. Then we pass to the modeling by Hill's criterion. For 12%, we calculated the Hill coefficients. And by applying the formulas, we got normal anisotropy modeled by Hill and planar anisotropy modeled by Hill for 12%. We know that the results of modeling by the Hill criterion is close to the predictions given by the Abacus software, and this for the two mechanical quantities on a deformation rate of 12%. Let's move to the second method, by characterization of the morphological texture of the material. Here we present image treatment processing workflow. We will present steps but in short. First step is to import images, as you can see here, for deformed state and recrystallized state. Then we have a very interesting option, ROI selection. Then we pass to quantitative and qualitative analysis. Then we have segmentation, and finally we get our results. First result here, we started by quantitative and qualitative analysis. We started by the measurement of the average grain size in the hardened and recrystallized state. You can see here the average grain size. Then we have grain size distribution in survey macrostructures for the two angles, 0 and 45%. For deformed and recrystallized state. Then we have segmentation, as you can see here, for the deformed state, and this is for the recrystallized state for the two cut angles. Conclusion: harmonious fluctuation in the variation of the flow stress curve along the three angles at different levels of strain, 2%, 8%, and 12% from experimental and simulation approaches. Then, it was observed that the effect of angle influences both the work hardened and the recrystallized states at the microstructural scale via the size and distribution of the work hardened and the recrystallized grain set and the probability density of grain distribution. That's it. Thank you for your attention.